Hi, today we're looking at linear programming. You'll find this in 7.5 out of our pre-calculus book. And we've been working with systems of equations and systems of inequalities, and today we look at the applications of those. So many applications of systems involve finding a maximum or a minimum quantity, and that's called optimization. And so that's what we're going to be working on today. Now, these problems will involve a couple things. First of all, there's going to be some sort of a linear objective function. This is what our goal is. Typically, this has to do with money. This is our objective is to make the most profit. And so we're looking for some sort of function that will find that for us. That's our objective function. All right. Also, along with that, we are going to have a system of inequalities called our constraints. These constraints, there might be one or two, well, there's going to be more than one, it's a system, but there'll be two, but probably more likely even more than that, 3 or 4 different inequalities that we have that are our constraints. And as you shade your inequality, it creates this enclosed polygon, something like this, and that's our feasible solutions, meaning anything in that shaded area ends up being a feasible solution for our objective function. All right, let's start with this kind of generic problem. There's not a situation really, they just handed us everything we need to know. Our objective function, z equals 3x plus 2y. We typically use a z for that objective function. And then we have this list of constraints. And on my little graph, I just gave you a little tiny graph here, but let's put in some axes. Let's just call this our y-axis right here. And I'm going to stick my x-axis about right in through here, mostly because I know where we're headed with this, and I'm going to want that. Okay, and so with that given, those are my x and y axes. Let's do a little bit of graphing. Okay, so this first constraint says x is greater than or equal to 0. Now that's going to be a vertical line with all of the x's that are greater than 0. So basically you're just shading everything to the right of that axis. Okay, and then the second constraint, y is greater than or equal to 0, is a horizontal line, and all of the y's that are greater than that. So basically that's just forcing you into your first quadrant. So now you're only dealing with this first quadrant. All right, the next two constraints have a little bit more going on. Let's take these and let's put them into slope-intercept form so that we could graph them. I'm going to move the x to the other side and divide by 2. All right, so then my y-intercept is a 2, and then my slope down 1 over 2. Do that a few times, get several points in there. It's an or equal to, so it's going to be a solid line. And I want all of the y's that are less than or equal to that, so that's going to be everything less than, which is this. And so now what I'm looking at is what's triple shaded, which is really just this little triangle here, because it was forced into the first quadrant by my first two constraints. And then the last constraint, let's put that one into slope-intercept form. I'm going to subtract the x to the other side and divide by -1. Remember that dividing by a negative will flip your inequality. And so then the y-intercept is a -1, and my slope is rise 1, run 1. And that point that right there it intersected, that's kind of important to find those points of intersection. It's a solid line. And I want all the y's that are greater than that, so that's going to go upward from here. But really what I'm looking for is where did it get shaded? And really this is quadruple shaded at this point because I have 4 constraints, and it is this region right here that becomes my feasible region. Now, when you have a feasible region there, it's going to have some vertices that create it. If you have 4 constraints, you're going to typically have 4 different vertices in your feasible region. Those 4 vertices at one of those points will be the spot that optimizes this function and this objective function that we have. So what you want to do then is come back and you're going to list out what all of your vertices are. So my first one I am looking at is over 0 up 2. And then my second one I see is I'm over 2 and up 1. And then I have one at over 1 up 0. and then I have another one that's at the origin. All right, what you do is you take each one of these are just ordered pairs, x comma y, and you plug them into this feasible region, I'm sorry, not this objective function that you have up here. All right, so on this first one, if I plug 0 in for x and 2 in for y, I would end up with a value of 4. Okay, on the second one, if I plug 2 in for x, that'd be 6 plus, plug 1 in for y, 6 plus 2 is 8. All right, and so you can kind of do this mentally if the numbers are small enough. If you need to type it in your calculator or write it all out, that would be good too. If I plug 1 in for x and 0 in for y, I'm going to get a 3. And if I plug 0, 0 in, I'm just going to get 0. All right, and so what I'm looking for is to find the maximum value. So that's going to happen right here because I got an 8 and that's the maximum value. So to optimize this situation, I would want to have my x value be a 2 and my y value be a 1. All right, let's try something where we have to come up with the constraints. So here we have a travel agent organizing this ski club trip, and she's arranging this for some men and for some women. But there are some constraints or some restrictions she has. So she can make arrangements for a maximum of 10 people. She has to have at least 4 men and at least 3 women in the group. And her profit is $12.25 for each woman and $15.40 for each man. So the question is how many men and how many women would give her her maximum profit. Okay, this is a pretty simple little one, not a lot going on here. That's kind of a good one for us to start with. Let's start with that objective function. I always think that that's kind of the easiest thing to pull out because it's the one that deals with money. Now, she makes $12.25 for each woman and $15.40 for each man. So let's let X represent the number of women that she's going to bring on this trip, and we'll let Y be the number of men on this trip. Then her objective function would be, well, let's see, her profit is $12.25 for each woman, so that'd be 12.25 times X plus, and then she makes $15.40 for each man, so $15.40 Y. And that's basically all there is that deals with money. So everything else is going to fall into the constraints. So looking at the constraints, it says that she can have a maximum of 10 people. So all of the women and all the men together cannot get greater than 10. So the constraint for that would be X plus Y has to stay less than or equal to 10. All right, the next constraint says there must be at least 4 men. Okay, so Y is men, so I have to have at least 4, so that's greater than or equal to 4. And at least 3 women, so that's X greater than or equal to 3. All right, so when I look at this graph, I can kind of tell that this is going to be forced into the first quadrant again just by those constraints. So I'm going to keep, maybe just to keep life simple, I'm going to just make this right here be my 2 axes. So basically my graph is the first quadrant. Okay, and so let's start graphing these constraints. I'm actually going to start with my 2 vertical and horizontal ones because they're kind of quick and easy. So Y is greater than or equal to 4. That's a horizontal line at 4, and I'm just going to scale by 1s here, I think is going to be easiest. So I want all the Y's that are greater than that, so that's everything up here. And then all the X's greater than or equal to 3, that's a vertical line at 3, and all the X's that are greater than that. Okay, so now I'm kind of looking at this box right here is where I've gotten it double shaded. All right. So let's look at this last one then. I'm going to put it in slope-intercept form as well and subtract the x. And so then that becomes y is less than or equal to negative x plus 10. Okay, I'm going to do this one maybe in pink so it stands out a little bit better. And so the y-intercept is at 10, right here. And then my slope is down 1 over 1. Okay, it's an or equal to, so I'll make it solid. And I want all the y's that are less than that, so that's everything down here. But most specifically, it creates this little triangle in here where it gets triple shaded by my 3 constraints. All right, I've got 3 constraints. I've got 3 vertices. Okay, so then we write those 3 vertices. I'm going to sneak it up here. So my first vertex is over 3 up 4. And then my next one is over 6 up 4. And then my other one is over 3 up 7. Now each one of these vertices that I found represent a potential spot where I'm going to be able to optimize this situation. And so I plug each one of those into my objective function down here. And so if I put 3 in for x, 4 in for y, plug that in my calculator, I end up with a 98.35. So that would be the travel agent's profit, 98.35. Or if we did 6.4, we would get 135.10. So that's a better deal. All right, and then the last one, if we did 3 and 7, she would make 144.55. Okay, so remember you're looking to maximize her profit, and so you're looking for the one that gets you the largest number back, which would be the 3.7, because she makes $144.55. All right, so let's look at what that means. That means the x is 3 and the y is 7. All right, so she needs to take 3 women and she needs to take 7 men to optimize or to maximize her profit. And so that really kind of should just make sense, because really she makes more money bringing men for whatever reason. Perhaps they spend more money or whatever the thing is. She makes more money. So she should bring as many men as she can, and since she was forced by a constraint to have at least 3 women, it makes sense. She's got her 3 women. The rest should be men. She'll maximize her profit. So that's a little bit of common sense there. This one was a simple enough one, again, that you kind of see that that should make sense. Be sure to come back and write kind of what the goal is. Maybe say take 3 women, take 7 men, and maximize your profit at $144.55. Come back and write a statement like that at the end. Okay, let's try one that's a little harder. Here's an example that has a lot more going on with it, and it's a little bit more confusing. A shoe manufacturer makes outdoor and indoor soccer shoes. There's a 2-step manufacturing process for both types of shoes. Each pair of outdoor shoes requires 2 hours of processing in step 1. Okay, so these are outdoor shoes, 2 hours of processing in step 1. So I'd put a 2 right here. I kind of sometimes organize this in a chart because it gets a little bit overwhelming with all the information. Okay, and then these outdoor shoes also require 1 hour of processing in step 2. So maybe it's like sewing and then gluing or whatever these steps are, but it takes 2 hours to sew, 1 hour to glue is what they're saying. Okay, now indoor shoes require 1 hour of processing in step 1 and 3 hours of processing in step 2. All right, so we've got that kind of organized, and here's where the constraint comes in. It says the company only has 40 hours of labor available in step 1. Okay, so step 1 right here has to maximize there at 40. I can't go over 40. And they only have 60 hours available for step 2. For whatever reason, for the employees or the equipment or whatever it is, that's where our constraint comes in. All right, the last piece is to create our objective function, and that's where the money part comes in. It says you got outdoor shoes that make a profit of $20, indoor shoes make a profit of $15, and so how many of each do you need? All right, so I'm just going to go ahead and make my indoor shoes be my X and my outdoor shoes be my Y. So let's see, outdoor shoes make a profit of 20, so that'd be a 20Y plus 15x. All right, I'll switch that around. So $15 for each indoor plus $20 for each outdoor pair. We'll come back to that objective function at the end. Okay, so now what we got to do is come up with our constraints. So our chart kind of helps us with those. And so for step 1, we're limited by 40 hours. And so I get 1 hour for each X, or each indoor shoe, so that'd be 1X, plus all the step 1 time that's spent on outdoor shoes, that would be 2Y, has to be less than or equal to 40. All right, what do you think your next constraint is? You go ahead and write what you think it would be. All right, ideally you put 3x plus 1y is less than or equal to 60. All right, that's just 2 constraints there. And the other thing that you have to do, and sometimes they give this to you and sometimes they don't, they need you to realize that you can't have a negative number pair of shoes. So the number of indoor shoes you have needs to be greater than or equal to 0, and the number of outdoor shoes needs to be greater than or equal to 0. And what those do is those pretty much just force you into the first quadrant. So I'm going to assume then, yes, I'm going to be in the first quadrant as I'm drawing this. So I've got this, and I've got this, and now I need to graph these other 2 equations. Okay, so we can start off and we can put them into slope-intercept form. So on this one, I'm going to subtract the x and then divide by the 2. So then y is going to be less than or equal to, subtracted the x, so it's going to be a negative 1/2 x plus 20. All right, this next equation, I'm going to put in slope-intercept form, so y is going to be less than or equal to negative 3x plus 60. Now I put these both into slope-intercept form, and then I'm going to go ahead and graph them. And the first 2, again, are really forcing me into the first quadrant, that x greater than or equal to 0, y greater than or equal to 0. The other 2, this one, I'm going to start at 20. And I'm going to go down 1 over 2. Now that's a little bit tricky with my scale, and your scale may be different, and that's okay, but what I'm going to do is I'm going to kind of up that. I'm going to call that 10/20ths. So I'm going to go down 10 over 20, and that takes me to there. Down 10 over 20. So adjust your slope so it'll work good for your scale. All right, drawing that line. You really, really are going to want to use a straight edge for this. We'll see how I do on mine, but you have to use a straight edge as you're drawing your lines, because you're going to be looking for where these 2 lines intersect, and you want it to be in a nice spot. Okay. That was not ideal at all. Okay, so let's see what the next one brings. Okay, so then I'm going to change the color. Oh, and I should say also that we're looking at all the y's less than that. So you're doing everything down this way. So now you're into that triangle. Okay, and so then my next equation starts at 60, and I have to go down 3 over 1, but I'm going to change that to down 30 over 10 and get a little bit nicer of a scale then. Down 30 over 10. Okay, and then you're going to draw your line. And again, definitely use a straight edge and get that to go through there. Okay, now my first line was not really great, and so if I were to redraw it, I'm just a little bit nervous. In fact, I think maybe it doesn't come out great even if I had drawn it nice. And so what I wanted to actually have that happen so that we could talk about what do you do when it doesn't cross nice and you really tried to graph it neatly. All right, well, I've got these 4 different points to create this feasible region in here, this little quadrilateral, and those are my 4 points that I'm going to check in my objective function. And 3 of them are pretty easy points to figure out. The other one there didn't come out very nice. If that happens to you, you do have to solve the system of equations. And so what you do is you take a little side note and go solve the system. All right, so I've got my system of equations. I'm going to take the top one times a negative 3. So then that gets me a negative 3x minus 6y less than or equal to negative 120. Bottom equation stays the same. X's eliminate. And actually, I have these inequality signs in here. As you're solving the system, remember, you're really just looking at where it is crossing, and so you're kind of really just thinking of it as an equal sign for right now. And so then that gets me negative 60. So y is going to be 12. And then take that, plug it in. I'm going to put it right there. So 3x plus 12 less than or equal to 60. So x, again, I have less than or equal to, but really I'm just looking at what it equals. And so the ordered pair there where those two lines intersect is 12, 16. Maybe yours cross nicer than mine, but this is what you do if it doesn't cross nice. You got to go solve the system to find that point. Okay, let's go back. So my 4 points that I have then are my origin, 0, 0. I have over 0 up 20. I have that point that I went and solved for, which was 16, 12. And then I have over 20 up 0. Those are my 4 points that I'm going to check in my objective function. All right, let's plug them each in and see what we get. All right, if we plug 0, 0 in, that's a pretty easy one. You're just going to get 0 back for that. All right, plug 0 in for x, and then 20 times 20 would be 400. And then if you put 16 times 15, and then 12 times 20, we get 480. And then the last one, if you plug 20 in for x, 0 for y, you'd get 300. All right, so it looks like to optimize our function, we've got this situation right here where I need to make 16x, 12y. So make sure you answer back, what does that mean? Okay, so to maximize the profit, remember that's your goal, maximize the profit, we need to make 16x, so that's indoor shoes. So you write a statement that says you need to make 16 indoor shoes, 12 outdoor shoes to maximize your profit at $480. Be sure that you write that sentence as your final answer. This one's a good example of using a table to help kind of organize your data, and I think that that's a great way when you start getting a lot of things going on. This example is about a furniture manufacturer making chairs and sofas, and they have different parts or different material that goes into making these sofas and chairs, and you're maybe not aware right up front where the constraints come into place, but you can at least kind of get it all organized here, and then you just put a total wherever the constraints come into play. So looking at this, it looks like I have all the information, and then it comes back and it says the manufacturer has room to store 1,300 packages of wood parts. And so when I look at this, that's really my total then for wood material. So I would put a 1,300 at this end. And then I'd have 2,000 packages of stuffing, so there's my total for that. And I have 800 packages of fabric, so that's my total there. So I'm going to be working horizontally here, creating my equations, because my totals or my constraints are about the material. Okay, the next thing that they tell me is the manufacturer earns $200 per chair and $350 per sofa. There's my objective function right there. Let's go ahead and start with that. So z would equal 200x plus 350y. All right, so the question is, how many chairs, how many sofas do they need to make to maximize their profit here? Okay, it looks like it was done kind of a little bit backwards. I said 200x, so that's my chairs. So really my x is the chairs and the sofa is my y. And so then let's come up with our equations for that. So the constraints look like it would be a 3y. This is for the wood. 3y plus 2x equals, actually does not equal. Let's get rid of that. We can't have any more, there's not space to store more than 1,300, so we want to make sure that that's less than or equal to 1,300. Okay, and then your next one is a 3y plus 4x is less than or equal to, oh, I wrote 200, but I'm sorry, I meant 2,000 there. So 2,000, and then my last one is a 2y plus 1x less than or equal to 800. All right, typically what we would do at this point is go put all of these in slope-intercept form and graph them, or maybe you could also use the intercepts method. We talked about that, which these are in nice standard form. Intercepts might work well. I want you to know that all of those are always options. Now, what we're actually going to try, though, on this one is I'm going to show you a third option. What if you just did this digitally? What if you and actually you could use your graphing calculator, but we're going to use a website to do this because it's pretty quick and easy to do. So what we're going to do is use Desmos.com to create this system of inequalities. Now what I'd expect to see is still a little graph of what you've got. So that feasible region we came up with kind of goes in here, and it swoops down, and then kind of swooped down a little bit more, and then it was really steep, and so it was kind of like this with some vertices right here and here and here and here and here, and so maybe we shade that in to show that that's the feasible region. Okay, but what I really want to do is go ahead and find what those ordered pairs were, and so if you'll recall that this ordered pair up here was over 0 up 400. And then this one down here obviously is 0, 0. This one over here was 500, 0. Okay, and then these were kind of the tricky ones that I was glad that I did this so that we could find them. This one here was 350, 200. And then this one up here was 200, 300. Struggling today, sorry. 200, 300. Okay, so those are the 5 points then that we're going to test back into our objective function. Okay, a lot of times I'm just doing that mentally. If you need to write that out, go for it. On this first one, I'm going to plug in 0 for x, 400 for y, and then do that kind of for each one of those ordered pairs. Why don't you take a minute and go plug those in and see if you can figure out which one of those points, which one of those vertices would optimize this situation and be able to help them maximize their profit. So pause the video for a second, go figure that out. Okay, so hopefully you ended up with 140,000, 145, 130, 100, and 0. So it looks like, though, that this is our best bet right here. And so you should have come back then and wrote a nice statement that says that you need to make 200 chairs and 300 sofas in order to maximize your profit at $145,000. All right, good job. Let's move on. Okay, so here this one is about filing cabinets, and we got floor space that we're limited. We got some storage capacity they're talking about. There is a little bit of money there. That's going to be our objective function. Again, this is one of those ones that probably has a lot going on. Let's set up a chart. Okay, so on this one, we are purchasing some file cabinets, and there's some file cabinets type A and some that are type B, and they hold different amounts, so their storage capacity is different, but they also then take up different amounts of floor space, so you have that, plus they cost different amounts, and so there was so much information there, I just kind of made up a chart of everything, and then let's just start filling it in. It says the office has 60 square feet of floor space for the cabinets. Okay, that's a grand total. That's going to be one of my constraints because I'm limited by floor space. So my total on floor space I can tell is going to be 60. Okay, and then the other thing that's weird about this one is that I also have a limitation on money. Not that that's weird, I got a lot of that going on, but $600 is in my budget. So I have a maximum here of $600. Usually that money goes into your objective function, but I think this one is going to be one of my constraints. It's one of my restrictions. Okay, so then it says cabinet A requires 3 square feet of floor space. So cabinet A, floor space, 3 square feet. and it has a storage capacity of 12 cubic feet. And it's going to cost $75. Cabinet B requires 6 square feet of floor space. It holds 18 cubic feet, and the cost is $50. Okay, so here's what we've got going on. This is going to be one of my constraints. This is going to be one of my constraints. But this one right here is actually what I'm trying to optimize. I'm trying to optimize my storage space. So that will be my optimization or my objective function. So it's going to be, I guess I'll call file cabinet A X, and I'll call file cabinet B my Y. So then it's going to be 12x plus 18y, and that's what I'll use for my objective function. Then my restrictions are actually going to be then 3x plus 6y. That's floor space. It's got to stay less than or equal to 60 because that's all the floor space I have. And then I also have a money constraint. I have $70 for each one of these plus $50 for each one of these, and it has to stay under $600. All right, we're going to have the obvious restrictions. X is going to have to be greater than or equal to 0. Y is going to have to be greater than or equal to 0. So you're dealing with just the first quadrant. Go ahead and scale your axes and set up a graph. You can use, it looks like on this first one, intercepts would work really nicely, but if you like slope intercept, you can do that too. As a third option, you could also use Desmos.com. Just decide, if that's the route you want to go, then you just have to sketch me a graph of what it gave you. All right, go ahead and finish up this problem. And so all of your note sheet should be completed. I want all of those problems done, and then you can continue on that same paper, look at the problems from the textbook for your homework, and all of it, notes and homework, all due tomorrow. Good luck.